All right, welcome class. Lesson 13.2. Before we begin today, I've been informed we need to practice an emergency lockdown drill. So that'll be our first EDL lockdown drill. So please close windows, lock doors, shelter in place until you get the all clear. All right, all clear. Here we go. Lesson 13.2. We're going to finish chi-square. Today is chi-square inference for two-way tables. Last time it was chi-square goodness of fit. That meant it was basically just a single list of data. You might recall back to chapter 5 when we did two-way tables. Two-way tables, we could have as many variables on the rows and the columns as we want, whereas yesterday we just had a single column or a single row. And this is what the TI-83 is capable of testing, is the two-way table. So we'll get to that when we get to an example. Okay, the null hypothesis for your two-way tables, there's no relationship between our row and column variables. And yes, we typically are going to be comparing several population proportions all at once. You might recall in previous chapters, we kept asking about, should we run multiple tests and then cherry pick the results that show significance? And we over and over and over said, no, that's not acceptable because type 1 error. Well, here's how I can use a single test and compare many proportions at once. So we're not magnifying the probability of a type 1 error. Again, the alternative hypothesis is that they're not all equal. That's different than saying they are all different. Okay, we're saying at least one of them is different. Okay. To get the expected counts, it's the row total multiplied by the column total divided by the table total. And our chi-square calculation is the same as it was yesterday. Observed minus expected squared divided by expected, and we take the sum of all those. Okay, degree of freedom is a little bit different for this test. Yesterday, for the goodness of fit, it was the number of categories minus 1. But now we have categories going two ways, hence two-way table. So it's the number of row categories or rows minus 1, the number of columns, again, each column will represent a new category, minus 1. Take the product of that. And that's why we can't use the chi-square feature on the calculator when I'm not doing a two-way table, because the number of columns is 1, and we would have 1 minus 1, 0. So if you try to use your chi-square feature on a goodness of fit, and you're not using the actual goodness of fit feature, it's going to say error because it's going to come out with a degree of freedom of 0. Okay, same requirement as yesterday. Our book is saying all counts, all expected counts need to be at least 1, and no more than 20% of our expected counts less than 5. Some books just say all of them at least 5. So again, it's kind of arbitrary on that requirement, but for our book, this is the way it goes. Okay, same deal as yesterday. If you find a significant result, you need to go back and check and figure out which categories were significant, showed a significant difference. So we call that an informal follow-up analysis. Okay, doing your follow-up analysis, go ahead and compare percentages. Hey, we expected this category to have 10% of the data, but we actually had 30% there. Or we expected this category to have 40% of the data, we only got 5% there. So compare what you observed and what you expected. You can use percentages, also observed and expected raw counts. And of course, it should be, where is it that we're finding these large differences? Don't spend your time saying, we expected 10% in this category and we got 10.2%. Every year I see students that do it for every single category. We don't want to be spending our time talking about where it was in line. We want to spend our time looking at where it's the most out of whack. Okay, the chi-square test can be broken down into two categories. One category is a test of homogeneity. Hopefully you guys know what that word means from biology, being homogeneous. When you do a test of homogeneity, you're comparing multiple populations and you're asking, are these populations homogeneous, meaning the same? Okay. Null hypothesis, proportions are equal, the same. Alternative, they're not all equal, different. Okay. The other test is a test for association or independence. This test, I'm taking a single population and then I'm breaking that population apart into various categories. So this test would be, I take a bunch of kids from, say, Irvine High, and then I break them apart by gender, by grade level, by whatever we think, AP, non-AP student, and see if there is a significant difference between these groups. But again, the groups all came from a single population. So then our null hypothesis would be everyone in the population is not associated, they're independent of whatever groupings or categorical variables that I picked, versus they are dependent. There is a relationship between gender and whatever. Okay. So those are the two ways to run a chi-square test. Again, homogeneity, I'm comparing multiple populations, right? So that would be, I take a sample from Irvine High, I take a separate sample from Woodbridge High, and I ask, hey, are high school students at these two high schools the same? Versus the association independence, I take one sample from one population and then I break that sample apart into different categories. All right, let's try a problem. I have some data here on reasons why men and women play sports. So we have different goals, and we've only broken it down by gender. So we have 2 column and 4 row categories. Okay. Please don't count the total as a category, right? I see some students will say, oh yeah, there's 3 columns, but no, there's 2 columns. Total is not a variable, right? It's just the sum. All right, so let's do it. These are, of course, the observed counts. So we have female, male. These are observed, or O. Okay, so there's our observed counts. Now we have to calculate our expected counts. Okay, sorry about that. Phone call came in and kind of cut us off there. Hopefully our phone is now turned off from calls. Yes, hopefully. Or we might have a 3-parter here. Okay, so here we are. We've got our observed counts. Those are given. Observed counts are always given. They must be given or you can't do the problem. To get your expected counts, think about it like this. 45 of the 134 people surveyed chose this as the reason why they play sports. So that proportion of the female should land in the expected female count. That proportion of the total male should land in the male expected counts. So that's why it's row total times column total divided by table total, or in other words, 45 out of 134, that proportion of females should land in this category, and that's how many females were surveyed. Of course, when you actually multiply that out, that's 1/2. So half of 45. And it's going to be that same proportion of males, or in other words, half of the 45 in that row should also be male. Okay. Now, this is the interesting case. I made it as our example because these are equal. Right? When these are unequal, you really do need to work out each individual calculation because it won't be, half and half. However, in this instance, it's just going to keep being half and half because the grand total over the column total is always 50%. So this is going to be 12.5, 12.5. And 13, 14, 19. Okay, so these are the expected counts. You can see the sum of the rows will match the sum of the rows on the observed. The sum of the columns will match the sum of the columns on the observed. They must. If they're not equal, it's not going to work. You've made a mistake. And your calculator, by the way, will even tell you error. They must be exact matches. So never round these off. If they come out to a non-terminating decimal, then leave it as the calculated fraction. All right, so now, null hypothesis, if I don't know if that got cut off or not. They're the same reasons. Alternative, different. In this case, they play sports for different reasons. All right, jump over and doing our calculation. Okay. Each cell has an observed count minus an expected count. We square it, divided by the expected count for that cell. So you're going to see, in this case, 1, 2, 3, 4, 5, 6, 7, 8 fractions because we have a 4 by 2, in other words, 8 cells, because it's a 4 by 2 two-way table. So calculate each cell, sum it up. There's our chi-square statistic. Our degree of freedom, the number of rows was 4, the number of columns 2. So 4 minus 1 times 2 minus 1 gives me an overall degree of freedom of 3. Looking on my table cuts off at 17.73. I've exceeded that. My statistic is well beyond the end of the table. The table ends with a p-value of 0.0005. Since I've exceeded that statistic, or my statistic has exceeded that table value, I know my p-value is less than 0.0005. Now, in the future, you're probably never going to calculate one of these entirely by hand. This is a small two-way table. Imagine a much larger two-way table. You can have many fractions to calculate, so perfectly acceptable on a free response question. Give me the first couple, and then just put ... and then report the answer, okay? And you're going to obviously get that answer from your calculator. Before we show you how to do it on the calculator, let's get to the informal follow-up. So, conclusion, we have very strong evidence to reject the null hypothesis. Therefore, we conclude that men and women, or male and female, individuals are playing sports for different reasons. Now, I need to figure out, well, what are those different reasons? Where do they differ? So I look at my observed counts. I look at my expected counts. Okay. I could look at the individual cells, and if it's just one cell or 2 cells, I should hit on those cells. But in this case, it's more of a global difference. You see that females have the majority of their data down here at the bottom 2 rows, meaning they're not very motivated for social comparison reasons. But males, on the other hand, the majority of their data are in the first 2 rows, meaning the male data is from high social comparison. So we're saying that men are going to be more motivated for social comparison reasons, women not motivated for social comparison reasons. So that should be our informal follow-up. Okay. All right, let's take a look at how to do it on the calculator. Right now I'm resetting my calculator so that it'll match what yours will look like first time. All right. So you would go to stat, you'd go to test, you'd find your chi-square test, and when you choose it, you see this new notation. This notation is matrix notation. Okay, you're not going to put the data into a list because it's a 2x2 table. Instead, you have to enter the data into your matrices. So the matrix menu is in yellow on the very left-hand side. It's above the X inverse key. You can rename your matrices if you really want. I just leave them the way they are. Go over to edit, choose that first matrix. The default is it's a 1x1 matrix, or in other words, just has one single entry. We want to change that. We want to have 4 rows, 2 columns. That's a 4x2. So I make this 4, 2, hit enter. I now have a matrix that matches the size of my 2-way table. Matrix A is going to be my observed counts, so I'm going to enter these 8 counts. Okay. Then go back to the matrix menu, go over to edit, go to matrix B, make it a 4x2, right? The sizes have to match exactly or the calculator can't do it. It's going to say error. Now I need to enter my expected counts. Again, do not round them off. In this case, they came out pretty clean, but in other cases, you will have to enter the fractional value, unrounded. Okay. Now that all the information is entered, I quit. I go back to stat test, chi-squared test, got my observed in matrix A, got my expected in matrix B, I calculate it, and there you go. There's your chi-squared statistic, just like we said. Here's the accurate p-value, and some of you hopefully have learned your lesson. This is not a p-value greater than 1. It is not a p-value of 1.6. P-values are never greater than 1. This is, of course, scientific notation. This is p-value of 1.6 times 10 to the -5th. And there you go. That's the chi-square test for 2-way tables. By office hours, flex time if you have any questions.